In this lesson, you're going to learn how to find the area under a normal curve. So a few reminders. A normal curve is unimodal and symmetric. We know by the empirical rule that 68% of your data is within 1 standard deviation of the mean. Within 2 standard deviations, so that's all 4 of these, would be 95, and then 3 standard deviations includes 99.7% of your data. We can use the empirical rule to answer many questions. One such example is the following. The distribution of heights of young women aged 18 to 24 is approximately normal with mu, your mean, of 64.5 inches and a standard deviation of 2.5 inches. So when given this, always begin by labeling your model as normal and fill in your parameters, your mean, comma, standard deviation, and then count off your standard deviations by adding 2.5 to the right, and then on the left, subtracting 2.5. We're asked about what percent of young women have heights less than 69.5 inches. So by the empirical rule, I know that 69.5 is 2 standard deviations to the right. And within 2 standard deviations, 95% of your data is contained. Well, that's 2 standard deviations on either side. So I need to chop that in half to get this region here. So that would be 47.5%. And then if I take this entire area to the left, well, since it's to the left of the mean, that's plus 50 more percent. So that's a total of 97.5%. Next, we're asked, is a young woman with a height of 62 inches, which would be 1 standard deviation below the mean, is she unusually short? And then we're to justify our answer. Well, just by looking at this, the area to the left, she would be taller than that percentage of people, whatever that area is. So let's use the empirical rule to decide that. So what I would do is I would find this area of 1 standard deviation. I always work off of the mean, away from the mean. This bit in here would be 34% because it's half of 68 by the 68, 95, 99.7 rule. So this over here would be 50% because it's to the right of the median. So if I did 100% minus the sum of 50 and 34 would be 84%. That would be 16%. So what would my conclusion be? So that tells me that a woman 62 inches tall would be taller than 16% of all women. So this is not unusually short. You may consider it short, but not unusually. Something in a very small percent, like 1% or 2%. That's unusual. Next, we're asked what percent of women are shorter than 60 inches. So when I look at this, 60 inches would be, somewhere right in here. What makes this challenging is that it's not located at a nice whole number for standard deviations. It's a little more than 1, but not quite 2 standard deviations below the mean. So in order to figure this out, I'm going to go and look at the standard normal distribution. So let's take a second and talk about a very special normal curve, which is the standard normal curve. It still has an area equal to 1, and the mean is in the middle, but the awesome part is it's super easy to draw because the mean is 0 and the standard deviation is 1. So I can easily count out my standard deviations very quickly. When I use the standard normal curve, I'm going to go to z-scores because that's going to tell me how many standard deviations away any of corresponding x value is. I can then use a table of values, which is kind of old-fashioned to find any of the areas under the curve, or your graphing calculator and a function known as normal CDF. I'll show you in a moment how to find normal CDF on your calculator. So to find what percent are shorter than 60 inches, I'm going to find how many standard deviations away by finding the z-score. So it would be 60 minus the mean divided by the standard deviation. That gives me negative 1.8, which makes sense. That's what it looked like. So on the standard normal curve, that would be right here, negative 1.8. And we're finding the area to the left of this. And now to find the area that corresponds to the left of negative 1.8, we're going to use a function called normal CDF on the calculator. There are 4 values that you'll need to enter into the calculator, which is your lower bound and your upper bound. So the lower bound means how far to the left you want it to calculate. Well, this area, remember, goes forever to the left, and you can't enter negative infinity into the calculator, so instead we're going to just enter a really small number, like negative 9,999. The upper bound would be the z-score of negative 1.8, and then the mean on the standard normal is 0, and the standard deviation is 1. Looking at the Calculate 84 app, which works for iPhones and iPads, there is WapidEmu for Androids, or of course, use a regular TI-84 graphing calculator. The normal CDF function is hidden in distribution, so you need to hit the second button and then vars, which is next to the clear. You'll then choose the second option, normal CDF, not PDF, normal CDF. And you've got to enter 4 values. The lower bound, the upper bound. Okay, so the area to the left goes forever to the left, so you enter a really small number. For my course, please enter negative 9,999, comma, you're going to the z-score of negative 1.8, and the standard normal curve has a mean of 0, and a standard deviation of 1. So it's lower bound, upper bound, mean, standard deviation, hit enter, and there you can see 0.036 approximately, or 3.6%. So now the notation that I expect you to use when solving these would be to write out that the probability that the z-score is less than negative 1.8 is equal to, write normal CDF, followed by your 4 values, your lower bound, your upper bound, your mean, and your standard deviation will always be 0 and 1 for the standard normal. Now, what percent of women are taller than 6 foot? So you need to change that to inches. That's going to be what, 72 inches? So this time, 72 inches, I just realized I made that a 70. That needs to be 72 right there. That falls exactly 3 standard deviations above, okay? So I wouldn't necessarily have to do it with normal CDF. I could just use the empirical rule because I know 99.7% is within 3 standard deviations, but I just want to show you that if you didn't recognize that right away, that this way would work, where you find your z-score, 72 minus 64.5, divided by, 2.5 gives me a z-score of 3. Okay, so you can then do normal CDF on your calculator. Proper notation would be the probability that your z-score is greater than 3 is equal to normal CDF and fill in your 3 numbers. Okay, but this time your lower bound is the area starts here at 72 and goes forever to the right, or you could say here starts at 3 and goes forever to the right. So you're going to put in 3, and then since it goes really far to the right, put in a big number, this time positive 9,999,001. Take a second, type that in your calculator, and check your answer. And when you do, you get 0.0013, or approximately 0.13%. Now, when we use the empirical rule, we would have gotten 0.15%, and that's because we're doing some estimating with the empirical rule. Normal CDF, because it's using technology, goes to more decimal places, and you're getting a more accurate answer. So that's why it's necessary to show me that you did it by normal CDF and not the empirical rule. In number 6, we're asked what percent of women are between 60 to 64 inches tall. So now if I go to my regular normal model here with the mean of 64.5, let's see, that's going to be, here would be 60. I'm finding this area in here. So it's a bounded interval. So I'm going to use normal CDF, so I'm going to find my z-score. I'm going to need two of them this time. Well, we already found it for 60. It was negative 1.8. My second z-score, I've got to find that one. 64 minus 64.5 divided by 2.5 gives me negative 0.2. So this time, for my probability statement, I'm finding the percent or the probability that my z-score is in between two values, negative 1.8 to negative 0.2. So this time, I'm going to do normal CDF, and my lower and my upper bound are z-scores. Take a second, type that in your calculator, check your answer. I get 0.3848, which is approximately 38.48%. Okay, here's a new scenario. SAT math scores follow a normal distribution with a mean of 511 and a standard deviation of 110 points. Suppose a student is chosen at random. What's the probability that the student scores less than 450? So here's the three-step process I want you to always do. You're going to make a picture, which means you're going to make your normal model. You're going to label it with the parameters. Do your best to make it unimodal and symmetric. So 511 is my mean, and 110 is my standard deviation. Take a second, pause the video, and fill in your standard deviation. In your picture, you want to label what it is you're trying to find. So a score less than 450, let's see, is probably about here. And you're doing the area, because it's less than, to the left of this. So, ballpark, your answer should be less than 50% because it's to the left of the mean. All right, next, so you can use your standard normal curve, you need to find your z-score. So a z-score of negative 0.55, that does correspond with my picture. So what are we trying to find? The percent or probability that my z-score is less than negative 0.55 is equal to normal CDF. Fill in your four numbers. And when I do this on the calculator, I get 0.2912 approximately, so that's 29.12%. Example 3, high levels of cholesterol in the blood increase the risk of heart disease. For 14-year-old boys, the distribution of blood cholesterol is approximately normal with mean of 170 milligrams of cholesterol per deciliter of blood and a standard deviation of 30 milligrams per deciliter. Cholesterol levels above 240 milligrams per deciliter may require medical attention. What percent of 14-year-old boys may require medical attention? And I specifically remind you to do your three-step process. So the first thing to do is sketch your normal model where it's approximately with a mean of 170 and a standard deviation of 30. Label your mean and your standard deviations. And those with 240, which would be about here, or above, may require medical attention. So that shaded region is the area we need to calculate. So next I'm going to find how many standard deviations from the mean that is by doing my z-score of 240 minus 170 over 30 gives me a z-score of approximately 2.33. So I'm going to say the percent or probability that my z-score is greater than 2.33 is equal to normal CDF. My lower bound this time is 2.33 and it goes forever to the right. So my large number is on the right, mean and standard deviation. And as a decimal, I get 0.099 or 0.99%, so it's less than 1% are going to require medical attention. Our last example, suppose student GPA follows a normal distribution with a mean of 2.9 and a standard deviation of 0.4. So as I'm reading, I'm already sketching. Approximately normal, 2.9, and 0.4. What percent of students would you expect to graduate with honors, which is cum laude? They always announce that at graduation. And over on the right, you can see the definition, which does vary sometimes from school to school, but cum laude is those who have between 3.5 and a 3.6 GPA. So I'm labeling my standard deviations on my normal model. So what percent are between the 3.5 and 3.6? So that's going to be an area right in here, 3.5 to 3.6. So this time I'm going to need to find two z-scores because it's bounded on the left and the right. So I'm going to do 3.5 minus the mean divided by the standard deviation, and then over on this one I need to do 3.6 minus the mean divided by the standard deviation. So I have my two z-scores, and good notation is I'm finding the probability that my z-score is between these two values. So 1.5 to 1.75. And again, I'm going to do this by normal CDF to find that shaded area. So I get 0.0267, which would be 2.67% of students we would expect to graduate with that honor. So not an awful lot.